Further discussion on the surface and normal, and then surface transformation, normal transformation. Okay, so we'll proceed. So this is Linux Mint. Okay, so discussion is on surface, normal transformation, surface transformation. Okay, how they are related to each other. So surface is area, surface is area, surface is an area. Surface needs at least 3 vertices. If 3 vertices are available, then it is a surface. Where a normal is a direction. Surface is an area. Normal is a direction. It has magnitude and direction. Normal is a vector. Surface is not a vector. Okay, surface can have direction, we can think about it, but it's not kind of, like normal. There is a difference. Like if I have 3 vertices, if I add edges, it becomes a triangle, and if I fill it, it becomes a surface. So surface has area. If I have only one point, this makes a normal, a vector. Means if I draw from the origin, if I draw okay, so from origin, if I draw a line, okay, so this is Mr. Origin, and if I draw a line from origin to this point, this line is the vector. So if this point is P, any P, then the vector equation will be P. Okay, this is one vector. So it has direction, we can see, and it has magnitude. Okay, so if it is okay, so if this point corresponds to P, okay, if this point corresponds to P, then this is a vector and its magnitude can be represented as P, or we can say like if it is XYZ, then x square plus y square plus z square, okay, and a square root. So x square plus y square, and then plus z square, and then square root. So this is also called Euclidean space. And then a square root. So that is also a kind of, so this is the magnitude of the vector. So that is P, or x square plus y square plus z square. So with one point also we can represent a vector, or if I have 2 points P1 and P2, then the line that is passing through P1 and P2, that is P1 minus P2. So that is the vector. Okay, now at a single point, if I draw a parallel to this line, okay, so if this is the line, if I draw exactly parallel to this line and it passes through origin, okay, then P1 minus P2, so P1 minus P2 is the new vector, P1 minus P2 would be some xyz, and that is, so if P1 is x1, y1, z1, P2 is x2, y2, z2, this would lead to x1 minus x2, y1 minus y2, z1 minus z2. So there will be x, y, z. This is net x, y, z. And that is, if I draw from the origin a line, so this is this vector. So if I have 2 points, P1 and P2, and a line passes through P1 and P2, that vector is actually this one. Not this one, what we think. Okay, the direction of vector is from the origin. If I have the net xyz, then this is the vector. So we have surface and this is the vector. So vector can be represented as one point, one vertices, and a line passing from origin to that point. So that is the vector. Okay, now we can calculate what would be its magnitude. So a vector has magnitude and direction. You can refer to a vector tutorial. Okay, what we want? Now, if I see the surface can be of two types, polygoned. Can we see so many polygons? These are square. Okay, so these are quad. This can be a triangular polygon also. Okay, so I can have a sphere. Okay, so this is a sphere. I can make it big. Okay, so this is a sphere, and now, okay, can we see now it's triangles? So earlier it is quad and then it is triangle. So a polygon, so a surface can be like it is a sphere and its surface can be set of polygons. That is what we are saying. Or it can be completely smooth. It is called analytic surface. Okay, so analytic surface is like which can be represented by an equation where this is set of polygon data. So these are polygon, 1 polygon, 2 polygon, 3 polygon, 4th polygon, 5th polygon, is set of polygon where this is analytical surface. Surface can be in both ways. Okay, so surface can be represented as, okay, polynomial equation. So I can say it as x, okay, x square plus y square plus z square minus k, or minus if it is unit, equal to 0. Okay, so this is the equation of this sphere. Any sphere, a square minus, okay. So a surface is up to 2. What we are planning to do now? So if I have two surfaces, kind of surfaces, what do we want? We want to calculate the normal. So that is the idea. Like at any point, what would be the direction of normal? At any point, what would be the direction of normal? Anyway, here at all points, direction of the normal are same. This is what we want to calculate. What is the normal? Okay, so what is the normal? What is the normal? So that is the question. Okay, so what is the normal? At any point, what is the normal? Now, the analytical surface, what we are saying, it is of two types. One is like we can define a surface, okay, that is kind of where the independent variable are 2. So it is kind of based upon S and T. So S is X kind of and T is Y and R is Z, STR. This is generally used in texturing. Okay, so this is a function VST and it has a kind of 3 points X, Y and Z. Sorry, 3 equations corresponds to this function. Okay, so X, Y and Z. Okay, so a function with kind of variation in ST, that is X, again Y, again Z. If that is the situation, if that is the polynomial equation, this is called explicit surface definition. And if I have in X, Y, Z equal to 0, then this is implicit surface definition. Okay. Now, we want to calculate the area of a surface. So, if this is a sphere, okay, now if I draw a sphere like this at any point, okay, if I do the derivative, differentiation along the S direction, so it will give kind of a tangent. If I do the differentiation along Y direction, it will give another tangent. Now, 2 tangents are available in S direction, in T direction. Okay. Now, it would look like perpendicular to each other, S and T. Okay. So, what we are trying to find is, we are trying to find one surface that will be kind of, now we are talking about a line that is tangent. Can we think about a surface? Okay. So, can we think about a surface? Okay. At any point, can we think about a surface? Okay. So, at any point, can we think about a surface that will kind of, I am not able to draw it nicely. So, that will just sit on top of it. So, this is the surface that is kind of sitting just on top of it. Okay. So, this is better drawn like this. So, now there is a surface that sits exactly on top of it, and at this point we can say, now I am saying this is a tangent in Y direction, in T direction, this is a tangent in X direction. Now we can say this as a surface at this point that is tangent at that point on the on the sphere. So a sphere is 3D, then its tangent is 2D. So if tangent is surface, then there are two vectors, this vector and this vector. We can say as V1 and V2. If we calculate cross of V1 and V2, we can calculate the normal. That is the story. So if I have a analytical surface 3D at any point, that is explicit surface definition, means that is variable only in S and T. And if that is the equation, if I calculate tangent in S direction and in T direction, so it would look like this at any point. This corresponds to two vectors. If there are two vectors, then they correspond to a kind of a surface. Okay. So if they correspond to kind of a surface, I can draw a surface like this. I believe this would be better. I can draw a surface like this. So this is nothing but a surface. Surface just exactly sitting on the sphere on 3D diagram. Okay. So that is the idea. So if I get the exact surface with the two tangents, then I can calculate the normal. Then here I can calculate the normal. So calculating the normal is nothing but, if I have two vectors, if I do the cross, then I get the normal. Okay, exactly like this. So if this one vector is like this, another vector is like this. Like if I have a triangle and one vector is like this, one vector is like this, the normal would be V1 cross V2. This is what we want. So in analytical surface, we calculate two tangents, and based upon the two tangent, we estimate the area, and that area okay. So that area we calculate the cross, and then that is the normal. This is the way we do. Now let's take example of a sphere. So VSTR, but actually it should be VST, but anyway, STR equal to 1. So this is the equation. So if I say R equal to 1 minus ST. Okay, so explicit way we have to specify VST. So this would be S in X direction, T in Y direction, and G any function ST in the Z direction. So that is like this. VST equal to ST. This is explicit differential. We are talking about explicit differential. So this is X, Y and Z, that is kind of dependent upon these variables ST. For a sphere it leads to like this, ST, then along the R it is 1 minus S square and T square the square. Okay. Now the vector V1, that is S and T, these two, we can calculate like dVST by ds and dVST by dt. Okay, if that is the case, then V1, the vector, now two vectors are coming, V1 and V2. So one vector would be 1. So if I differentiate with S, this would be 1, this would be 0. And this would be 1 minus S square minus T square to the power 1 by 2. So that will be 1 by 2 into 1 minus S square minus T square to the power minus 1 by 2. So there is a chain rule, and then we will differentiate again. So that will come as minus 2S. So 2 we can cancel, and then it will lead to minus S into 1 minus S square minus T square to the power minus 1 by 2. That is the way we do the chain rule in the differentiation. And just for the brevity, we have not added the calculation. So now it would be 1, 0 and minus S and cross. So this is V1. and this is V2. If this is V2, then the differentiation of S, now we are calculating V2. So dVst by dt, so this is the differentiation. So this would be 0, this would be 1, and this would be again 1 by 2, 1 minus s square minus t square to the power of minus 1 by 2. Please refer to differentiation calculus tutorial, differentiation and integration. And minus 1 minus s square minus t square to the power minus 1 by 2, because we have to minus 1, 1 by 2 minus 1 is minus 1 by 2. Then again chain rule, it will be minus 2t, so it will lead to minus t by minus s1 minus s square. So these are two vertex we are getting. So we are getting s and t. If we are getting two vertices that constitute to a surface, then normal will be cross of these two. Okay. Now the cross of these two, that there is a formula for that. If this is A, B and C, A1, B1 and C1, this is A2, B2 and C2. So there is a formula to calculate, and we calculated. This would lead to something like I believe so, like okay, so A2 and okay, A1 2 and B2 3 minus something like that. Okay, so that is the cross. So we calculated, and it comes to minus s by this, t by this and 1. So this is the normal what we are talking. So we got the normal. So in s direction normal is this, in t direction normal is this, and in z direction normal means in r direction normal is 1. So we will do the normalization. So normalization is nothing but what normal we calculated by its magnitude. Okay, so magnitude is nothing but, okay, so magnitude, if we want, then this square plus this square plus this square to the square root. So that will lead to s square plus t square plus 1 by 1 minus s square minus t square to the square root. Then it will finally come to like this. If this is true, then it will be s by, okay, so now we have to divide n by magnitude, so that would lead to s by this, t by this, and then 1 minus s square t square this. If I see only the direction, then it will come as st and like. So this is the, finally we are getting normal at any point s, t and the GST, GST, okay, so S, T and GST. So S, T and GST is this. So this is the normal we are getting. Now we will calculate. If n is, can we see the elegance? This is, we have not mentioned. The elegance of explicit formula is, we don't have to worry about the points. Point we can just place and we get the, means it is just amazing. Okay, so I can just give 1 0, x, s direction 1 and y direction 0. It would lead to 1 0 0. So s direction 1, 1, y direction 0, and then it would lead to 1 minus 1 0. So it will be 1 0 0. So here in s, this point we are talking 1 0. So it will be outwards, that is the normal. This is what we want. In y direction it will be like this, and where z is 1 and xy are 0, it will be like this. Okay, now at places where both are 0.5, 0.5, okay, so it will be somewhere here, okay. Okay, so what we are saying is something like this. Okay, somewhere in x direction here, and then inside y, okay, some direction here, and then it will be, I believe it is understandable. So it would be inside the sphere, it will be at this point, and then in z direction we have to think, okay, but okay, so now we don't have to worry about z. This is the class of this explicit definition of the analytical surface. I just say x and y 0.5, 0.5, then it is 0.5, 0.5 as per the equation st, and 1 minus s square and t square. So 0.25, 0.25, 0.25, 1 minus 0.5, 0.5 to the square root. So that would come as 707. Okay. What about 0.5 and 0? So in x direction 0.5, y direction 0, we don't worry about where it hits on the top. But it will be greater, okay, than this z. So it will be 0.50, 0.866. So t is 0, s is 0.5, this will 0.25, and then 1 minus 0.25, 0.75. Okay. Import math dot square root, okay, 1 minus 0.5 into 0.5, 0.866, So if we are on x-axis, then z will be more. If we go towards y-axis, okay, then z will be lower. So that is the idea. At the center, both will be kind of okay. So center, at the center there is nothing. Means I believe there won't be any surface touching. So other point that we calculate. Okay, so we finished the analytical surface, explicit surface definition. Now what we need to do is we have to find the surface equation that is based upon S and T, not in R. S, T and GST. Once we get, then we have to do the differentiation and we calculate the two vector, and after calculating two vector we do the cross. Once we find the new normal, we do the normalization and we get the actual normal direction. We are talking about normal direction, this one, not this one. If we do P1 minus P2, it leads to the actual vector direction. Okay, normal is a vector. Okay, vector has its own rule and regulation. It's not that easy. Okay, it can make someone's life hell, this vector direction. Okay, now we'll see, so we finish this, now we'll see the implicit definition, implicit surface definition. Now if this is a surface, I mean a sphere, then implicit surface definition leads to fxyz equal to 0. Okay, and then we have to calculate the formula like this: x square plus y square plus z square minus 1 equal to 0. Now we find the gradient in x, in y and z. If I calculate like this, 3 gradients, net gradient, then we can get the normal. So easy. So that will be 2x, 2y and 2z in direction of x, y, z. Relax. So this is far better than explicit, but there is a caveat. Caveat is estimating x, y, z. It is very difficult. Here it is in equation of 2 only. S and T. Here it is x, y, z, and it is very difficult. So this is better. means we get in the kind of in variation of only s and t. Here I have to calculate xy. So getting the actual point on all point on surfaces to calculate the normal is very difficult. Anyway, but we'll do. Can we see it is similar? S, t, and if I say 1 minus s square by t square, it is x, y, z. It is similar. Anyways, now if we have find x, y, z, then x 0, 1, 0, 0, it will be 1, 0, 0. 0, 1, 0, it will be 0, 1, 0. And 0, 1, it will be 0, 0, 1. Exactly like this, what we calculated. Here we calculated with this formula 1 minus s square t square. Here it is direct, but we have to find. Now this is difficult, the way we are saying. Now if x is 0.5, y is 0.5, what will be z? So that we have to calculate based upon this formula. And then at that point, the normal would be 5.5 and this lead to 0.707. So it is exactly like this. So this is the way we calculate the polynomial analytical surface normal. Okay, there are two ways. One way we calculate the gradient, okay, and for direction of x, y, and z, and calculating the points are difficult. But here in explicit, we just say s and t and gst, and then we calculate v1 and v2. If we get v1 and v2, we calculate the cross to get the normal as per the vector analogy. And once we get cross, we do the normalization and we try to get the actual normal direction, and then we do. Okay, so next we'll see how to find vertex normal in the polygon data. Then we'll see much awaited. So surface normal we calculated, much awaited normal transformation. The relationship between surface transformation and normal transformation. Okay, so if I rotate this, okay, if I rotate this, translate this, rotate, translate, or scale the surface, what about the normal? I mean, what I am trying to say, if I do the transformation on the surface, how much transformation we can receive on the normal? So both are not same. Transforming the surface and transforming the normal are not same. If I transform the surface, same transformation matrix I cannot apply on the normal. So what is the relationship? Okay, so that we'll see.